In previous videos, we showed how such an inequality leads to the proof that W11 of balls are contained in the high-wash class. In other words, using the right-hand side and the fact that it is bounded by the maximal function of the gradient, we produce the high-wash gradient for classical Sobolev functions. In this video, we see a different consequence of this type of pointwise inequality. Let's recall for precision what this inequality is claiming. You have any ball in Rn, and this range of P. Probably this equality is also allowed, but we're not looking for optimal results here. So if you have a Sobolev function on the ball, in particular, we're not assuming it's compactly supported there. So you can imagine that U is a function actually on a larger domain. Then at almost every x in the ball, the difference, the oscillation of the function is bounded by this object, which by now you recognize as the Riesz potential of the gradient. Again, we used it to easily show that then the function U has a high-wash gradient. We will now use this inequality to prove a Poincare inequality for such functions. And that relies on this boundedness fact, that the Riesz potential is an LP to LP bounded operator. And this is true for every open domain. So if you have a bounded open domain in Rn and you define the corresponding Riesz potential, so to be precise, we could add the symbol here, but it just makes the notation horrible. So given G, we define its Riesz potential over omega the same as before, except that the integration is over this region, not all of Rn. So it's then true that this operator takes LP integrable functions to LP integrable functions with the bound that is a measure of the open set to power 1 over n times a constant that depends only on dimension n and the power p. This lemma has an interestingly short proof, despite how significant it is. So I hardly contained my excitement to cut out the proof from this video at least. But if you really want to see it, I can do one, or you can read it all by yourselves from Kinnunen's lecture notes, which I have mentioned many times. So Juha Kinnunen from Aalto University has some notes under the name of Sobolev spaces. And I will make a separate video about this because they also have a book which is an expansion of similar topics. Anyway, so once you have this pointwise estimate star and this boundedness, you can easily obtain a proof of the so-called PP Poincare inequality. The PP Poincare inequality, the repetition PP is that you take P norm, P integral of the oscillations, and then it's bounded by the P norm of the gradient. So you could have different factors Q and Q here, then it will be a QP Poincare inequality. So this is one of the significant inequalities. Remember, we talked about what makes Sobolev functions special, and one of the items was that they do satisfy inequalities of this sort. Also, Sobolev inequality when the domain is all of Rn. We will talk about that one in the next video. So let's see how these two lemmas above give an easy proof of this one. First, notice that when omega is a ball itself, then the measure to power 1 over n is basically just the radius of the ball. Just that's because volume of ball is r to power n basically. And that constant difference can be absorbed into this C and P. Okay, so from lemma 1, we know that for almost every point x, we have this pointwise inequality. And so we want to estimate the LP norm of the left-hand side. So you take to power p, you integrate and you take pth root. So this will be, this is none other than LP norm of u minus u b. But then, because of this pointwise inequality is true almost everywhere, this is less than or equal to the LP norm of the Riesz potential of the gradient u. But now lemma 2 comes in, and this says that this is bounded by a dimensional constant, radius of the ball, and then the LP norm of the gradient. So technically, you want to take absolute value to make it a scalar function, and then take LP norm, which is none other than this side, except for the averages. But notice that we can just remove these averages because the powers match. So this average becomes tricky if we have different powers on either side. But this inequality is equivalent to the same inequality with the average removed. So it's written this way because when it's QP, Poincare inequality, then it does matter. And that's the end of the proof, really. It's just the rewriting of that inequality. So this is again an important inequality, and direct proofs of this are available, but also quite calculational. Lots of Hölder inequalities, Fubinis. But the thing that I like about this type of proof is, number one, once you have a pointwise inequality, you just forget about this side, the left-hand side, and you only deal with this object, which we have seen time and again that is a very nice, well-behaved operator, for example, by this boundedness. And this approach has been emphasized in the book by Joaquinonen and co-authors that I mentioned, and they obtain not just this PP Poincare inequality, but many, many families of inequalities through the same techniques and analysis, also using the fact that the Riesz potential is bounded by, if this is a ball, then it's bounded by the radius times the maximal function of g. And the book, I think, is titled Maximal Function Approach to Sobolev Spaces or something like that. Again, I will make a video about that one. And I'll give you the exact titles and year. But this type of approach is so uniform. One thing that bothered me with reading up classical Sobolev theory was that when you had a proof of, say, Sobolev inequality for range between 1 and n, you see a kind of very different proof compared to when you see, so when you have Sobolev inequality, which gives that the LP star is bounded by constant the LP norm of gradient. And when you see PP Poincare inequality, also known as Sobolev Poincare inequality, so the inequality we just proved can be regarded as a Sobolev Poincare. So Sobolev inequality is when you have a function on all of our n, and the Sobolev Poincare inequalities are when you have functions on bounded domains, for example, the ball. And for these functions, because constant functions pose a problem, that's why you always have this u minus b. Here you don't have that one. So the constant functions are ruled out by the fact that these are defined on all of our n, and constant functions that satisfy w1p are only the constant. So the function has to die down at infinity. Anyway, so what I was saying, that when you see proof of this Sobolev inequality, and then you see proof of, say, PP Poincare inequality, the techniques are kind of very different. So as if they are different phenomenon. And also there is then Riesz inequality, where for this range strictly bigger than n, you prove that the function is actually Hölder. And again, there you see kind of a different type of proof. But this approach based on pointwise estimate and Riesz potential and maximal function, in the work of Johan Kinnunen and co-authors, has given all of these very uniform proofs. For example, in the next video, I will focus on the Sobolev inequality, and that you can obtain by a similar proof to above, except that you need to first prove a stronger boundedness, and that is that LP star of our n, Riesz potential, is actually bounded by constant the LP norm of G. So it's not LP to LP bounded, the Riesz potential. Actually, it's LP to LP star bounded. We also had mentioned this before. And when you have this one, very similar argument gives you a proof of the Sobolev inequality. Also, that helps prove a version of this very same inequality here with P star, which is also commonly known as the Sobolev Poincare. So you don't have to say QP, because P star in this case is the Sobolev conjugate. So this is called Sobolev Poincare. So it's a Sobolev inequality in that we have P star, and it's Poincare because it's on the ball and not all of our n. So it has both of the two theorems of Sobolev and Poincare. Therefore, these are called usually Sobolev-Poincare inequality. So yeah, anyway, once you get any good estimates on Riesz potential, it translates to proving classical embedding theorems about Sobolev functions. So if any part of this you want more information about, any of these parts you want proofs of, let me know. And see you in the next one, talking more about the Sobolev inequality, but same techniques. Thanks for watching and have a great one.